let's go to the second oral session. And this time we will have 4 speakers. The first one is Pramit Saha. He is a postdoc from University of Oxford, and the title is Federated Finetuning of Visual Language Foundational Models. Let's welcome Pramit.
Thank you. Hello, everyone. I'm Pramit. I'm a postdoc in the Department of Engineering Science in the University of Oxford. And I primarily work in biomedical image analysis. So I'm going to be talking a little bit about fine-tuning vision language foundation models in the context of healthcare. This is our sweet little team in University of Oxford, where we are focusing on this kind of projects. The work that we are going to talk about today is going to be a collaboration across this. Okay. One of the main challenges that we face in healthcare is availability of data. That's the main challenge, limited data availability. So what can we do to tackle the problem? If I don't have enough data, then I would like to collaborate with other institutions that might acquire similar type of data. But the problem in healthcare, though, is that data sharing is getting more and more stricter. I mean, it's getting harder, right? The privacy preserving aspect and the patient sensitive data. So one way of tackling that is, instead of collecting all data in a centralized location, we try to deal with it using federated learning, where we distribute the model to the different individual clients. Now, that's a problem because the institutions that we collaborate with, for example, the hospitals or healthcare clinics, would not have the kind of resources that we would want to have to tune foundation models. So this talk is going to be about how can we enable foundation model fine-tuning in low-resource environments using federated learning, for example. So for those of us who are new to federated learning, it's a way of decentralized machine learning, where instead of collecting the data all together in a centralized server and training your model, you instead send your model to the individual clients. And so we'll be talking about 2 different types of parameter-efficient fine-tuning, that is additive fine-tuning and selective fine-tuning. Okay, data. So we investigate 2 different settings. So let's say I have 5 different clients here, which are representations from 5 different data sets, which are mixed modality data sets, meaning that each client will have different radiological data sets like chest X-ray, CT, ultrasound, MRI, and so on and so forth. And the other setting that we have here is based on a data set that we curated. It's more than 700,000 samples of medical images. It's basically triplets of visual, question, and answers. So if you're interested in working with challenging VQA data sets, feel free to contact us. We'll be happy to help. And here we curate modality-specific data sets as different clients. That is histopathology and MRI and CT and so on and so forth. And you can see the domain gap across these different modalities. Right? So that makes the task very challenging to fine-tune models. So the first thing that we did is we looked at a benchmark. So we first tried to see how these different parameter-efficient methods work when we try to fine-tune vision language models in our healthcare settings to solve the different VQA tasks. Could be open-ended, could be closed questions, right? So we see, of course, it varies, but generally we find that adapter-based methods work pretty well, works better than the other methods in fine-tuning under federated learning context. But we also saw that there is a difference. If you notice, there is a difference. There's a marked difference between the full fine-tuning, which is the first one, versus the last one, which is the the best. I mean, the last few ones, which are based on adapter-based methods. What we would like to do is fill the gap between full fine-tuning and parameter-efficient fine-tuning in federated learning settings. So how do we do that? We first try to figure out what are the problems associated with adapters in federated learning. What we see here is the adapters are generally very unstable because they're learning so much information, so much varied information from these varied or different clients, that they end up getting very confused, and the training process is not very stable, as you can see from the loss curve here. So we are trying to tackle that by aligning the adapters. So what we are trying to do here is when we collect the adapters from these individual clients and take it to the server to aggregate the adapters, we first say, before we fuse or before we aggregate the adapters, let's first align the adapters. So we do that using a permutation technique. It was published in AAAI earlier this year, where we take the help of optimal transport theory, and then we use it to compute differences between or distances between the neurons into adapters, and use that to realign the adapters in such a way that they are closer. As you can see, if you look at, for example, here, I'll just show here. If you look at these two adapters and you want to aggregate the adapter, you lie in a high loss area in the loss landscape. Whereas if you first permute it or align it to your anchor adapter and then average it, it improves the performance because it lies in a low loss area now. And this leads to an improvement in performance. We get near full fine-tuning performance with this one. And as you can see, the loss curve improves, and we achieve better convergence. We were thinking, can we reduce it further? For example, if you look at a lava model with a 32 layers, that means 32 adapters. Can we select where to place adapters in the lava? Or if we want to just do selective fine-tuning, we have 32 layers. Which layers should we fine-tune in this resource constraint setting under federated context, because you are in a collaboration now? What we are trying to do is develop a two-step procedure where we are saying, first, let's focus on your own data, and based on your own data, figure out what layers do you want to select. So find some metric that is a good reflection of the importance of different layers, and based on that, select which layers you want to fine-tune. Secondly, because you're a part of a federation, take advantage of the other clients as well. So learn from others as well. So have a consensus across which layers should be selected across which clients, instead of just deciding by your own. So we use the neural tangent kernel as a metric. So we use the principal eigenvalue of neural tangent kernel computed layer-wise, because that's known to be the main one of the dominant factors towards convergence. And that's why we select this metric and then decide this to be the driving factor behind choosing which layers we want to look at or fine-tune in a given client. And as you can see, the distribution of these eigenvalues across different layers. So if you have 32 layers, the eigenvalues will be varied from one layer to another, and based on that we select. So this is the structure where we have individual clients. Let's have 2 clients here, and I compute the eigenvalue of individual layers, and based on that I select which layers I want. But that's client level. So if we want to take advantage of the federation, what we could do is, instead of selecting it in the clients, we send the scores of individual layers to the server and let them talk. So we develop a multi-objective optimization here, where we say not only do we want to select the layers which are best for the individual clients, but also overall for the federation, meaning that we don't want to always select the same layers, for example, across all the clients, even if they want to, because we want to diversify the information content or the information extracted through the training procedure as a result of this federation. And as a result, you will see that the layer selection is being diversified. The darker ones are the more important ones, and the yellowish ones are the less important ones. And you'll see that now varies, which was previously more uniform, by taking advantage of this federation. And you'll see that initially we were only looking at a few layers in the federation, whereas now if we take the advantage of this server level optimization strategy, then we can spread it a little bit farther, so that we can include more and more layers into the federation that incorporates more information in the training process. And as a result, what we see is our method that we call focus is giving better performance. It shows better discrimination in the TSNE space for the VQA as well. We find that it reaches closer performance to all adapters. So here in this experiment, what we did is we selected adapters based on these different pruning techniques, structured pruning techniques, and our method. And we show that selectively fine-tuning adapters, like I showed, actually reaches similar performance as having all adapters in the space. And that's quite consistent across different settings. For example, if you select, let's say, 2 layers across all clients, versus if you select heterogeneously, that is 4 layers in one client and 2 layers in another client and 7 layers in other clients and so on and so forth. So the result is quite consistent across different settings based on your choice. We show the computational versus performance trade-off. And as you can see, focus, of course, has a little bit of lesser performance than the full fine-tuning, and often less than adapters as well. But if you look at the parameter space as well as the communication space, because in federated learning we also deal with communication across different clients, you'll see that this leads to much less resource requirement and communication demand, well, along with the performance boost. So we compare our method with different types or different ways of selecting layers or selecting adapters, and it shows quite good performance. Overall, I think federated learning shows us or gives us a method to fine-tune foundation models in healthcare settings, because then we can collaborate and gather more data this way. But also it adds some more challenges, like the data heterogeneity, modality heterogeneity, task heterogeneity, and so on and so forth across different clients. One of the main methods to tackle that is probably aligning whatever parameters you're taking from individual clients or individual sites before combining or merging the parameters or the model in general. First, maybe try to align the models closer to each other and then aggregate. So add an extra step before that. And if you're in a federation, take advantage of the consensus across different clients and try to maximize the total information content extracted from the data by talking to each other. So that's the main idea. Thank you so much.
Due to time limitation, we'll have a web question. Any question?
Thanks a lot. Really interesting. I was curious about the privacy side. So you talked about the VQA benchmarks, but have you tried to jailbreak the models, or because I appreciate there's not many parameters you're fine tuning, but at the same time, it seems like that would be a concern, possibly.
Yes, there are different. Well, that's a prevalent research direction in federated learning as well. And there are concerns like the leakage, for example, or gradient leakage, or things like that. People do use things like differential privacy and homomorphic encryption and so on and so forth to try to tackle that. I did not personally try to look at that, but there are separate fields or studies that look at that detection. In general, I think if the main concern is whether the data can be reconstructed back, then a few typical like safety precautions during training will help. For example, if you have a higher batch size, for example, that helps to make sure that not a single sample can be reconstructed back, but it will be more like a sort of like a representation, because if you have a larger batch, then it becomes harder to reconstruct. So things like that can be followed during the training procedure itself to tackle that, I think.
Okay, thank you.
Thank you.